In the vast theater of the cosmos, where reality bends and breaks under the weight of gravity, there exists a phenomenon that challenges our understanding of the universe itself. We live in a world filled with voids and absences, from the mundane to the magnificent. Yet among all the cavities that perforate our reality, none captivate the imagination quite like the enigmatic structures that inhabit the darkest corners of space, the cosmic holes that defy comprehension and reshape the very fabric of existence. For decades, astronomers and physicists have pondered the nature of black holes, those gravitational monsters from which nothing, not even light, can escape. These are the ultimate prisons of the universe, regions where space-time curves so dramatically that all paths lead inward, toward an infinitely dense point called a singularity. But the story of cosmic holes extends beyond these lightless abysses. There exist theoretical constructs, born from the equations of general relativity, that suggest the universe might harbor even stranger entities. White holes represent the mathematical opposite of their black counterparts, hypothetical regions that expel matter and energy rather than consuming them. While mathematically permissible within Einstein's framework, white holes remain purely theoretical, with no known mechanism for their formation and no observational evidence supporting their existence. They stand as mathematical curiosities, solutions to equations that may never manifest in physical reality. Yet between the absolute darkness of black holes and the theoretical radiance of white holes lies something altogether more intriguing, a theoretical object that occupies the twilight zone between these extremes. These are the gray holes, exotic stellar remnants that represent one of the most fascinating possibilities in theoretical astrophysics. Neither wholly black nor entirely transparent to radiation, gray holes embody an ambiguous state of gravitational extremity that challenges our categorization of cosmic objects. To understand where gray holes fit in the cosmic hierarchy, we must first explore the progression of stellar death, that inevitable transformation that awaits every star in the universe. Stars are not eternal. They are temporary beacons, burning through their nuclear fuel over timescales ranging from millions to trillions of years. What remains after a star's fiery death depends critically on the mass it possessed during life and the mass that survives the violent throes of its demise. At the lower end of this stellar afterlife spectrum, we find white dwarfs, the fate that awaits our own sun approximately 5 billion years from now. When medium-sized stars exhaust their nuclear fuel, their cores collapse until a remarkable quantum mechanical effect halts further compression. This phenomenon, known as electron degeneracy pressure, arises from the Pauli exclusion principle, which forbids electrons from occupying identical quantum states. As the stellar core contracts, electrons are forced into ever higher energy states, generating an outward pressure that counteracts gravity. The result is a white dwarf, an Earth-sized ember containing roughly the mass of the sun, glowing softly as it radiates away its residual heat over billions of years. White dwarfs represent a remarkable state of matter, with densities approximately 1 million times greater than water. A single teaspoon of white dwarf material would weigh several tons on Earth. Yet despite their impressive density, white dwarfs are relatively spacious compared to what comes next in the hierarchy of stellar remnants. When stars more massive than about 8 solar masses reach the end of their lives, they undergo catastrophic collapse, leading to supernova explosions that briefly outshine entire galaxies. If the remaining core mass exceeds approximately 1.4 solar masses, the Chandrasekhar limit electron degeneracy pressure proves insufficient to halt gravitational collapse. The core continues to contract until protons and electrons are forced together, creating neutrons in a process called neutronization. At nuclear densities, neutrons themselves become degenerate, generating neutron degeneracy pressure that can finally arrest the collapse. The result is a neutron star, one of nature's most extreme creations. These objects pack approximately 2 solar masses into a sphere merely 20 kilometers in diameter, creating densities comparable to atomic nuclei. A neutron star is essentially a single, gigantic atomic nucleus, held together not by nuclear forces, but by gravity. The density is so extreme that a sugar cube-sized sample would weigh approximately 100 million tons. On the surface, gravity is 200 billion times stronger than on Earth. The magnetic fields surrounding neutron stars can exceed the strongest fields produced in terrestrial laboratories by factors of trillions. Neutron stars represent an almost unimaginable state of matter, yet even they are not the ultimate expression of gravitational compression. As we venture deeper into the realm of theoretical physics, ascending the ladder of density toward the limits of what matter can withstand, we encounter increasingly exotic possibilities. Among these theoretical constructs are electroweak stars, hypothetical stellar remnants predicted to exist at densities approximately 100 times greater than neutron stars. These objects would measure perhaps 5 kilometers across, while containing multiple solar masses. The physics governing electroweak stars enters a regime far beyond our everyday experience, where temperatures and densities become so extreme that the electromagnetic and weak nuclear forces normally distinct merge into a unified electroweak interaction. At the core of an electroweak star, temperatures would exceed what is known as the electroweak temperature scale, approximately 1,000 trillion degrees. Under these conditions, matter undergoes transformations that have not occurred naturally in the universe since the first trillionth of a second after the Big Bang. Exotic particle reactions occur continuously, generating immense quantities of energy in particles that create an outward pressure. This radiation pressure represents the last barrier against total gravitational collapse, the final mechanism by which matter can resist the inexorable pull of gravity. Electroweak stars occupy a precarious position on the edge of stability. Add more mass, compress them further, and the critical limit is reached. Space-time itself begins to cave in under the gravitational strain. The curvature of space-time becomes so extreme that it forms a region from which nothing can escape an event horizon surrounding a black hole. At the center lies a singularity, a point of infinite density where the known laws of physics break down completely. But theoretical physics suggests there may be one more step. One more exotic possibility in this progression from stellar remnant to black hole. If we could somehow compress an electroweak star to densities approximately 1 million times greater still, without quite crossing the threshold into black hole territory, we might create something unprecedented, a gray hole. Gray holes, also known as Q-stars in the technical literature, represent a theoretical middle ground between the most extreme neutron stars and the event horizons of black holes. The name Q-star derives not from quarks or quantum mechanics, as one might reasonably assume, but from a conserved particle number, a technical detail that reflects the sometimes whimsical nature of scientific nomenclature. This naming convention might seem arbitrary, but it follows a long tradition in taxonomy and physics of labels that often obscure more than they reveal. The defining characteristic of a gray hole is its relationship to the Schwarzschild radius, that critical distance from a mass at which the escape velocity equals the speed of light. For any given mass, if you compress it within its Schwarzschild radius, you create a black hole. A gray hole exists at the very edge of this boundary, with a physical surface radius perhaps 5% larger than its Schwarzschild radius. This narrow margin makes all the difference. A gray hole is not quite compact enough to form an event horizon, yet it is compact enough that light can barely escape its gravitational grip. Consider what this means for the behavior of light near a gray hole. If you could somehow stand on its surface holding a flashlight, a thought experiment requiring indestructible equipment and immunity to gravitational forces that would instantly obliterate any known material you would discover, that light behaves in profoundly counterintuitive ways. The intense gravitational field curves spacetime so dramatically that most directions you might aim your flashlight would not allow the light beam to escape. Point the flashlight horizontally, parallel to the surface, and the light beam would curve downward, falling back to the surface. Aim it at a shallow angle upward, and the same thing happens, gravity bends the light's path into a trajectory that returns to the gray hole. Only if you aim the flashlight almost perfectly perpendicular to the surface, within a very narrow cone of directions, will the photons manage to escape the gravitational field and reach the outside universe. This narrow range of permitted escape directions is called the escape cone, and it represents the defining observational signature of a gray hole. To a distant observer, a gray hole would appear similar to a black hole in most respects, a dark sphere surrounded by an accretion disk of superheated matter spiraling inward. But unlike a black hole, which is perfectly black within its photon sphere, a gray hole would emit a faint glow from its surface, a dim reddish light escaping through the narrow escape cone. The light that manages to escape from a gray hole undergoes extreme gravitational redshift. Photons climbing out of the intense gravitational well lose energy. Their wavelengths stretch toward the red end of the spectrum and beyond. Light that originated as high-energy gamma rays, or X-rays, might emerge as visible red light, or even infrared radiation. This dramatic redshift, combined with the narrow escape cone that allows only a small fraction of emitted light to reach the outside universe, means that gray holes would appear extremely dim, despite the enormous energies involved at their surfaces. The similarities between gray holes and black holes extend beyond their appearance. Both possess photon spheres regions where gravity is strong enough that light can orbit the object in circular or spiral paths. Both would be surrounded by accretion disks if matter is falling toward them, creating brilliant displays as gravitational energy converts matter into radiation. Both create extreme gravitational lensing effects, warping the appearance of background stars and galaxies. To a casual observer, distinguishing between them would be extraordinarily difficult. Yet, there are crucial differences that become apparent when matter falls into these objects. Consider an unfortunate astronaut falling toward what appears to be a black hole. As they approach a true black hole, something remarkable happens from the perspective of a distant observer. Time dilation becomes so extreme near the event horizon that the falling astronaut appears to slow down asymptotically, never quite reaching the horizon, gradually fading from view as their light becomes increasingly redshifted. From the perspective of the distant observer, the astronaut takes an infinite amount of time to cross the event horizon. From the astronaut's own perspective, however, the experience is quite different. They would cross the event horizon in finite proper time, unaware of anything particularly special about that moment. Inside the event horizon, all paths lead inevitably to the singularity at the center. The astronaut would be torn apart by tidal forces, the differential gravitational pull between their head and feet, long before reaching the singularity, in a process colorfully termed spaghettification. Falling into a gray hole would be an altogether different experience. From the perspective of the distant observer, the falling astronaut would still appear to slow down and redshift as they approach the surface, just as they would near a black hole's event horizon. But crucially, the astronaut would actually reach the surface in a finite amount of time from the observer's perspective. They would not freeze at the boundary and gradually fade from view over eons. Instead, they would impact the surface. The impact would occur at relativistic speeds, with the astronaut traveling at a significant fraction of the speed of light when they strike the gray hole's surface. The collision would be catastrophic, instantly converting the astronaut's mass and kinetic energy into radiation and elementary particles. The impact would generate an enormous burst of heat at the collision point, with temperatures potentially exceeding those in the cores of massive stars. Most of this energy would remain trapped by the gray hole's gravitational field, unable to escape the narrow confines of the escape cone. But a small fraction would emerge as a faint afterglow, briefly visible to distant observers before fading. This afterglow would represent the final observable signature of the astronaut's demise, a flash of light escaping through the narrow window that gravity permits. This raises a profound question about the nature of gray holes. Black holes are not composed of matter in any conventional sense. Once matter crosses the event horizon, it contributes to the black hole's mass, charge, and angular momentum. but it loses all other properties, what physicists call the no-hair theorem. The interior of a black hole is a region of severely warped space-time, terminating in a singularity. There is no surface, no structure, just the geometric properties of curved space-time itself. Stars, in contrast, are definitively composed of something atoms of hydrogen, helium, and heavier elements, held together by gravity and supported against collapse by the pressure generated from nuclear fusion or quantum degeneracy. Stars have surfaces, interiors with varying compositions and temperatures, and complex internal structures. What then of gray holes, which occupy the boundary between these two extremes? Are they composed of nearly ordinary matter, perhaps exotic states of conventional particles compressed to extraordinary densities? Or are they more akin to black holes, representing geometrical features of spacetime itself? The answer, according to theoretical models, is neither, and somehow both. Theoretical physicists propose that gray holes would be composed of something called a scalar field, a concept that requires some unpacking. In physics, a field is a mathematical function that assigns a value to every point in space and time. The electromagnetic field is a familiar example, describing the strength and direction of electric and magnetic forces at each location. A scalar field is simpler in some ways, assigning just a single number to each point in space-time rather than a direction or multiple values. The Higgs field, which permeates all of space and gives fundamental particles their masses, is perhaps the most famous example of a scalar field. The Higgs field has a non-zero value throughout the universe, and excitations in this field, ripples in the cosmic ocean, so to speak, manifest as Higgs bosons, the particles detected at the Large Hadron Collider. The field itself is an ocean of potential, and the bosons are waves upon that ocean. For a gray hole, theorists propose that the entire object would be composed of a hypothetical scalar field, distinct from the Higgs field but sharing some similar properties. The gray hole would represent an enormous concentration of this field, a coherent configuration stabilized by its own gravity. There would be no atoms, no electrons, no neutrons, none of the familiar constituents of ordinary matter. Just an intense, self-gravitating scalar field configuration. This might sound like pure abstraction, but scalar fields are not merely mathematical conveniences. They represent real physical entities that can store energy and momentum, interact with gravity, and exhibit particle-like excitations. The key to understanding how a scalar field could form a stable, compact object lies in the quantum mechanical properties of the bosons associated with the field. The fundamental particles of nature divide into two categories based on their quantum mechanical behavior: fermions and bosons. Fermions, which include electrons, protons, and neutrons, obey the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state simultaneously. It is this principle that creates electron degeneracy pressure in white dwarfs and neutron degeneracy pressure in neutron stars as you try to compress fermions into a smaller volume. They resist because they cannot all occupy the same low-energy states. Bosons, in contrast, are not constrained by the exclusion principle. There is no quantum mechanical limit to how many identical bosons can occupy the same quantum state. In fact, bosons have a tendency to condense into the same state, a phenomenon known as Bose-Einstein condensation. This property of bosons has profound implications for scalar field objects like hypothetical gray holes. Because the bosons comprising a gray hole can occupy the same quantum states, there is no degeneracy pressure to limit compression. The scalar field can be compressed to extraordinarily high densities, potentially approaching or even exceeding nuclear density, the density found in atomic nuclei and neutron stars. This allows the object's radius to shrink to just barely above the Schwarzschild radius, without forming an event horizon. The gray hole sits at the knife's edge between a massive quantum object and a black hole. This configuration of a self-gravitating scalar field is sometimes called a boson star, when it exists at lower densities and larger radii. Boson stars are hypothetical objects composed entirely of bosonic fields, held together by their own gravity and stabilized by quantum pressure rather than thermal pressure or degeneracy pressure. They represent solutions to the combined equations of general relativity and quantum field theory, existing as stable or quasi-stable configurations. Gray holes, in this framework, represent the most compact possible boson stars configurations, compressed almost to the black hole limit. The term Q star, mentioned earlier, specifically refers to these ultra-compact boson star configurations where the letter Q denotes a conserved quantum number associated with the scalar field. These theoretical objects push the boundaries of what is physically possible without forming an event horizon. The theoretical possibility of gray holes raises an immediate question: how would they form? If they exist, what astrophysical processes could create them? For black holes and neutron stars, we understand the formation mechanisms quite well. Massive stars undergo core collapse when nuclear fusion can no longer generate sufficient pressure to counteract gravity. The result is either a neutron star or, if the core mass is sufficient, a black hole. For gray holes to form through stellar collapse, something extraordinary would need to occur during the collapse process. Somehow, the ordinary matter comprising the stellar core protons, neutrons, electrons would need to convert into the exotic scalar field that comprises a gray hole. This transformation would represent a phase transition of unprecedented scope, converting familiar baryonic matter into a completely different form of energy and substance. Current physics provides no clear mechanism for such a conversion. We have no experimental evidence that ordinary matter can transform into scalar field configurations, nor do we understand what conditions would trigger such a transition. The temperatures and densities achieved in stellar collapse are extreme by everyday standards, but they may not be extreme enough to induce the kind of exotic phase transition required. Moreover, even if such a conversion mechanism existed, the collapse would need to proceed with extraordinary precision. The stellar core would need to collapse at exactly the right rate, achieving exactly the right final density to create a gray hole rather than a black hole or neutron star. Collapse slightly too fast or too far, and spacetime curvature would exceed the critical threshold, forming an event horizon and creating a conventional black hole. Collapse in a non-uniform manner, and the asymmetries would likely lead to black hole formation as well. This requirement for precision makes gray hole formation seem improbable through natural astrophysical processes. The parameter space that leads to gray hole formation, if it exists at all, appears to be extraordinarily narrow. It would be like trying to balance a pencil perfectly on its point. Theoretically possible, but practically unlikely to occur by chance. These uncertainties place gray holes and Q stars firmly in the category of theoretical curiosities, rather than established astrophysical objects. Mathematics and physics do not prohibit their existence in the way they prohibit faster than light travel or violations of energy conservation. The equations of general relativity combined with appropriate scalar field theories admit gray hole solutions. But the existence of mathematical solutions does not guarantee that nature actually realizes those solutions. This situation is similar to that of wormholes, another exotic prediction of general relativity. Einstein's equations permit wormhole solutions, hypothetical tunnels through spacetime connecting distant regions of the universe, or even different universes. Yet we have no evidence that wormholes exist in nature, no known mechanism for their formation, and significant theoretical reasons to doubt their stability, even if they could somehow form. Gray holes occupy a similar theoretical space. They are permitted by the equations, intriguing in their properties, potentially revolutionary in their implications, but currently lacking empirical support, a clear formation mechanism, or observational confirmation. They exist primarily in the calculations of theoretical physicists and the speculative discussions of cosmologists. Nevertheless, the search for evidence of gray holes continues, driven by the tantalizing possibility that some observed astrophysical objects might actually be these exotic entities rather than conventional black holes. The challenge lies in finding observational signatures that could distinguish gray holes from black holes, no easy task given their similarities. The faint reddish glow from the escape cone represents one potential signature. A true black hole emits no light from its event horizon, though it can be surrounded by brilliant accretion disks and jets. A gray hole would additionally emit dim light from its surface. Detecting this subtle difference would require extraordinarily precise observations, likely involving techniques like very long baseline interferometry that can resolve incredibly fine details. Another potential signature involves gravitational wave observations. When compact objects merge, whether neutron stars, black holes, or hypothetical gray holes, they emit gravitational waves, ripples in spacetime itself, that carry information about the merger event. The gravitational wave signal from gray hole mergers might differ subtly from black hole mergers, particularly in the ring-down phase after the merger, when the remnant object settles into a stable configuration. Some researchers have speculatively suggested that certain observed X-ray binary systems, such as V400 and Force Cygni and Cygnus X1, which are believed to contain stellar mass black holes, might actually host gray holes instead. These systems exhibit complex variability and energetic outbursts that could potentially be explained by gray hole models. However, conventional black hole models also explain these observations adequately, and there is currently no compelling reason to prefer the gray hole interpretation. The theoretical framework surrounding gray holes connects to broader questions in fundamental physics, particularly concerning the nature of dark matter, the mysterious substance that comprises approximately 85% of the matter in the universe, yet remains undetected directly. Some physicists have proposed that dark matter might consist of ultralight bosons forming large-scale Bose-Einstein condensates, effectively creating scalar field structures similar to boson stars on galactic scales. If this scalar field dark matter hypothesis is correct, then the universe might contain a hierarchy of scalar field objects, ranging from galactic-scale dark matter halos down to compact boson stars and gray holes. The physics governing these objects at different scales would involve the same fundamental scalar field, merely configured differently based on local conditions. This connection between gray holes and dark matter remains highly speculative, requiring numerous unverified assumptions about the nature of dark matter and the properties of hypothetical scalar fields. Nevertheless, it illustrates how theoretical investigations of exotic objects like gray holes can intersect with major unsolved problems in physics and cosmology. The study of gray holes also connects to efforts to develop a quantum theory of gravity, one of the central unsolved problems in theoretical physics. General relativity describes gravity geometrically as the curvature of spacetime and works magnificently at large scales. Quantum mechanics describes the behavior of particles and fields at microscopic scales with extraordinary precision. Yet these two pillars of modern physics remain fundamentally incompatible in their current formulations. Black hole singularities represent regions where this incompatibility becomes acute. At the center of a black hole, densities and curvatures become infinite, and general relativity predicts its own breakdown. A complete theory of quantum gravity would presumably resolve these infinities, providing a description of what actually exists at the black hole's core. Gray holes, lacking event horizons and singularities, might avoid these quantum gravity problems. If they exist, they would represent the most extreme compact objects describable by current physics without invoking quantum gravity. Their surfaces, though incredibly dense and strong in gravitational field, would not reach the point where space-time curvature becomes infinite. They would exist entirely within the realm of classical general relativity combined with quantum field theory, avoiding the need for a complete quantum gravity theory. This characteristic makes gray holes particularly interesting as theoretical laboratories for exploring the limits of known physics. By studying the properties of these maximally compact objects that still avoid event horizon formation, physicists can probe the boundary between classical and quantum regimes for gravity, potentially gaining insights into what a full quantum gravity theory might look like. The progression from white dwarfs through neutron stars to electroweak stars, and potentially gray holes, represents an exploration of matter and spacetime under increasingly extreme conditions. Each step up this ladder of density reveals new physics and challenges our understanding of how matter behaves when compressed far beyond everyday conditions. White dwarfs taught us about electron degeneracy and the importance of quantum mechanics in astrophysical contexts. Neutron stars revealed the behavior of matter at nuclear densities and demonstrated that neutrons could form macroscopic quantum objects. Electroweak stars, if they exist, would probe the unification of fundamental forces under extreme conditions not seen since the earliest moments of the universe. Gray holes would represent the ultimate endpoint of this progression before black hole formation, the densest possible objects with surfaces, the strongest possible gravitational fields without event horizons, the nearest approach to the Schwarzschild radius that an object can achieve while remaining accessible to the outside universe. They would be the ultimate expression of gravity's ability to compress matter while still preserving some form of material existence. The study of such exotic objects might seem like an esoteric pursuit disconnected from practical concerns or even mainstream astrophysics. Yet throughout history, theoretical investigations of seemingly abstract phenomena have repeatedly yielded profound insights and practical applications. Einstein's development of general relativity initially seemed like pure mathematical physics with little practical relevance. Today, general relativistic corrections are essential for the GPS satellites that enable global navigation. Similarly, quantum mechanics began as an attempt to understand atomic spectra and other seemingly obscure phenomena. It became the foundation for modern electronics, computing, medical imaging, and countless other technologies. The investigation of exotic astrophysical objects follows this tradition, pushing the boundaries of understanding into extreme regimes where new physics might emerge. Moreover, the universe itself serves as a laboratory capable of creating conditions impossible to replicate on Earth. The Large Hadron Collider, humanity's most powerful particle accelerator, achieves energies of about 13 trillion electron volts in its particle collisions. Impressive as this is, cosmic ray particles regularly strike Earth's atmosphere with energies millions of times higher. Neutron stars routinely maintain magnetic fields billions of times stronger than any produced terrestrially. If gray holes exist, they would represent natural laboratories for physics at densities and gravitational field strengths far exceeding anything humans could create artificially. Observing and studying such objects, if they can be identified, would provide invaluable data about how matter and spacetime behave under the most extreme conditions imaginable. The challenge, of course, is finding them. With current observational capabilities, distinguishing gray holes from black holes appears extremely difficult. The faint surface emission from gray holes would be challenging to detect against the brilliant backgrounds of accretion disks and surrounding matter. Gravitational wave signatures might offer better prospects, particularly as instruments become more sensitive and our theoretical understanding of gray hole dynamics improves. Future observatories operating across the electromagnetic spectrum, from radio waves to gamma rays, might identify unusual systems that could be gray hole candidates. The Event Horizon Telescope, which produced the first images of black hole shadows, might one day image objects that show subtle deviations from black hole predictions, potentially revealing gray hole surfaces. Advanced gravitational wave detectors, both ground-based observatories like LIGO and Virgo, and future space-based missions like LISA, will observe mergers and other violent events involving compact objects with increasing sensitivity. The detailed gravitational wave signatures from these events encode information about the object's properties. Systematic differences between observations and black hole predictions could hint at gray hole or other exotic object involvement. The search for gray holes also illustrates the interplay between theory and observation in modern astrophysics. Theory suggests exotic possibilities that emerge from the mathematical framework of physics. Observations constrain which possibilities nature actually realizes. The conversation between theory and observation drives scientific progress, with each informing and challenging the other. Currently, theory says gray holes might exist. Observations have not yet confirmed or ruled out their existence. This situation could change in several ways. We might detect clear evidence of gray holes, confirming this theoretical prediction and opening new areas of investigation. We might instead find strong evidence against their existence, perhaps through precise observations that show all candidate objects behave exactly as conventional black holes predict. Or we might remain in uncertainty for decades or longer, with gray holes occupying the same ambiguous status they currently hold, mathematically possible, observationally unconfirmed, a tantalizing possibility that drives continued investigation but resists definitive resolution. Science often proceeds through such extended periods of uncertainty before breakthrough observations or theoretical insights clarify the situation. Regardless of whether gray holes exist in nature, their theoretical investigation serves valuable purposes. Exploring these exotic solutions to Einstein's equations deepens our understanding of general relativity and its implications. Studying the properties of ultracompact scalar field configurations advances our knowledge of quantum field theory under extreme conditions. Developing observational strategies to distinguish gray holes from black holes sharpens our measurement techniques and theoretical predictions. The broader lesson is that the universe likely contains phenomena stranger than we have yet imagined. Every major advance in observational capability has revealed previously unknown types of objects and phenomena. Before the 1,960 seconds, neutron stars were theoretical curiosities. The discovery of pulsars, rapidly rotating neutron stars, transformed them into observed reality and opened entire new fields of study. Similarly, black holes transitioned from mathematical abstractions to accepted astrophysical objects through decades of accumulating evidence, culminating in direct detection of gravitational waves from black hole mergers and direct imaging of black hole shadows. What currently seems exotic or unlikely may become tomorrow's established science. In this context, gray holes represent more than just a specific theoretical prediction. They symbolize the ongoing quest to understand nature's extremes, to map the boundary between the possible and the impossible, to explore how matter and spacetime behave when pushed to their limits. They remind us that the universe contains realms far stranger than everyday experience suggests. Consider what it might mean if gray holes exist. It would imply that nature has found a way to create objects almost as compact as black holes without actually forming event horizons. It would suggest that scalar fields, entities we currently understand only abstractly, play concrete roles in cosmic architecture. It would provide natural laboratories for studying quantum field theory under conditions of extraordinary gravity and density. The existence of gray holes might also have implications for the ultimate fate of black holes themselves. According to Hawking's theoretical work, black holes should very slowly evaporate through quantum effects, emitting thermal radiation and gradually losing mass. For stellar mass black holes, this process would take incomprehensibly long times, far exceeding the current age of the universe. But in principle, a black hole might eventually evaporate completely. Some theoretical models suggest that as a black hole loses mass through Hawking radiation, it might not simply evaporate to nothing. Instead, as it approaches the Planck mass, the scale where quantum gravitational effects become dominant, it might transition into a different configuration. Could a nearly evaporated black hole become a gray hole? Current theory provides no clear answer, but the question illustrates how these exotic objects might connect to fundamental questions about quantum gravity and black hole thermodynamics. The investigation of gray holes also connects to philosophical questions about the nature of scientific knowledge and the status of mathematical predictions. Science proceeds through a dialogue between theory and experiment, mathematics and observation. Theories make predictions that observations test. But what do we make of predictions that are mathematically rigorous, yet currently untestable, or testable only with extraordinary difficulty? Gray holes occupy this ambiguous territory, along with concepts like the multiverse, cosmic strings, and various other theoretical constructs that emerge from well-established mathematical frameworks, yet resist observational confirmation. Are they science or speculation? The answer depends partly on epistemological perspective and partly on pragmatic considerations about what lines of investigation prove fruitful. From one perspective, any mathematically consistent solution to verified physical theories deserves serious consideration as a possibility nature might realize. General relativity has been tested extensively and confirmed to extraordinary precision. Scalar field theories are well established in quantum field theory and particle physics. Solutions to these equations combining both frameworks should be taken seriously as potential astrophysical objects. From another perspective, the vast majority of mathematically possible configurations probably do not exist in nature. Mathematics is more permissive than physics. The universe must follow mathematical rules, but it need not realize every mathematical possibility. Without observational evidence or a clear formation mechanism, gray holes might be mathematical artifacts rather than astrophysical realities. These competing perspectives need not be mutually exclusive. Gray holes can be simultaneously taken seriously as theoretical possibilities worth investigating and treated with appropriate skepticism pending observational evidence. Science advances through this balanced approach, imaginative theorizing, constrained by empirical reality, bold hypothesis, tempered by rigorous testing. The story of gray holes reminds us that the cosmos remains largely mysterious despite centuries of astronomical observation and decades of space exploration. We have mapped the visible universe to impressive scales, observed galaxies billions of light years away, detected gravitational waves from merging black holes, and probed the cosmic microwave background from the universe's infancy. Yet fundamental questions remain unanswered. We do not know what dark matter is, despite overwhelming evidence for its existence. We do not know what dark energy is, despite its apparent dominance of cosmic dynamics. We do not have a quantum theory of gravity. We do not know if black hole singularities actually exist, or whether quantum effects resolve them. We do not know the ultimate fate of the universe, or whether other universes exist beyond our observational horizon. Gray holes represent one small piece of this larger puzzle of cosmic mysteries. They might exist or might not. They might be observationally accessible or forever beyond our ability to detect with certainty. But their theoretical investigation expands our understanding of what is possible, sharpens our thinking about extreme physics, and perhaps prepares us for discoveries yet to come. As we look toward the future of astrophysics and fundamental physics, several trajectories seem clear. Observational capabilities will continue improving dramatically. Gravitational wave astronomy, barely a decade old, will mature into a rich field probing cosmic events previously invisible. New generations of telescopes across all wavelengths will achieve unprecedented sensitivity and resolution. Computational capabilities will enable simulations of increasingly complex astrophysical phenomena. These advancing capabilities will either detect evidence of exotic objects like gray holes, or increasingly constrain their possible existence. Either outcome advances knowledge. Detection would revolutionize our understanding of compact objects, and possibly require new physics. Non-detection at high sensitivity would rule out certain parameter spaces and models, clarifying which theoretical possibilities nature actually realizes. Meanwhile, theoretical physics will continue exploring the mathematical framework of general relativity, quantum field theory, and candidate quantum gravity theories. New solutions might be discovered, existing solutions better understood, connections between different theoretical frameworks elucidated. The mathematical landscape of physics will become richer and more fully mapped. Perhaps future theoretical breakthroughs will reveal clear formation mechanisms for gray holes, elevating them from exotic curiosities to astrophysically plausible objects. Or perhaps deeper analysis will show that subtle effects prevent their formation or destabilize them, explaining their apparent absence from observations. Theory and observation will continue their dialogue, each informing the other in ways we cannot fully predict. In contemplating gray holes and similar exotic theoretical constructs, we glimpse the profound strangeness of reality at its extremes. The universe revealed by modern physics bears little resemblance to everyday experience. Space-time curves and warps. Particles exist in superposition states. Quantum fields permeate all existence. Black holes form from collapsed stars, creating regions from which nothing escapes. And perhaps, just perhaps, gray holes exist at the very edge of possibility. Objects so compact that light barely escapes, composed of exotic scalar fields, representing the ultimate compression of matter before space-time itself tears. Imagine, for a moment, a future where humanity has developed the capability to journey through the cosmos, visiting the exotic objects that current generations can only observe from afar. You are approaching what appears to be a black hole, drawn by scientific curiosity and the desire to witness one of nature's most extreme phenomena. Your instruments show intense gravitational fields, a brilliant accretion disk of superheated matter, the characteristic signatures of a massive compact object. But as you draw closer, your sensors detect something unexpected, a faint reddish glow from what should be the absolute darkness of an event horizon. The photon sphere and accretion disk appear as predicted, but the central darkness is not complete. A subtle cone of dim red light emerges from the object's surface, photons barely escaping the gravitational abyss. This is the signature of a gray hole. You have found not a black hole, but its exotic cousin, an object at the very edge of gravitational collapse. The realization brings both wonder and concern. You are observing something that exists only in the most extreme conditions nature can create without forming an event horizon. You are seeing the surface of an object, composed not of familiar matter, but of an exotic scalar field configuration. As you approach the boundary of safe distance, the gravitational forces intensify dramatically. Time dilation becomes significant clocks aboard your vessel, tick noticeably slower than those of distant observers. Light from the outside universe appears blue-shifted and compressed into a narrowing field of view as the gray hole's gravity warps space-time around you. The accretion disk becomes a ring of fire surrounding your view. You know that unlike a black hole, crossing too far means not gradual time dilation toward an event horizon, but direct impact with the surface. There is no gentle asymptotic approach, no infinite time dilation protecting you from the inevitable. Cross the threshold of stability, and you will fall to the surface in finite time, colliding at near-light speed with a configuration of scalar fields so dense they defy comprehension. The impact would disintegrate you into elementary particles, converting your mass into energy in a brilliant but brief flash. Most of that light would remain trapped, unable to escape the narrow confines of the gray hole's escape cone. Only a faint afterglow would signal your fate to distant observers. You would become one with the gray hole, your matter converted to its exotic scalar field, indistinguishable from the structure you sought to study. This scenario remains firmly in the realm of speculation and science fiction. Whether gray holes exist, whether humans will ever develop the technology to visit such objects, whether the theoretical framework describing them correctly captures their properties, all remain profoundly uncertain. But the scenario illustrates what these objects would represent if they exist: the ultimate expression of gravity's power, the boundary between accessible universe and sealed-off singularity, the strange twilight zone between neutron star and black hole, the journey from white dwarfs through neutron stars to electroweak stars, and finally to gray holes, traces a path through increasingly extreme physics. Each step reveals new aspects of how matter and space-time behave when pushed beyond familiar limits. Each step demonstrates that the universe contains states of existence profoundly different from anything encountered in everyday life. We live in an era of extraordinary discovery in astrophysics and cosmology. Gravitational waves have opened an entirely new window on the universe. Advanced telescopes reveal cosmic history back to the first galaxies. Precision cosmology constrains the universe's composition, geometry, and fate. Yet for all these advances, profound mysteries remain. And exotic possibilities like gray holes remind us how much we have yet to learn. The search for gray holes continues, driven by theoretical curiosity and observational capability. Future detections or definitive non-detections will further constrain our understanding of compact objects and extreme gravity. Whether gray holes prove real or remain mathematical abstractions, their investigation enriches our comprehension of physics at its limits. In the end, gray holes represent more than merely another type of hypothetical astrophysical object. They symbolize the ongoing human quest to understand nature at its most extreme, to map the boundaries between the possible and the impossible, to explore realms far beyond everyday experience. They remind us that the universe contains or might contain phenomena stranger and more wonderful than we have yet imagined. Whether you are a professional astrophysicist modeling exotic compact objects, an amateur astronomer contemplating the night sky, or simply someone curious about the universe's mysteries, gray holes offer a window into the extraordinary creativity of theoretical physics and the profound strangeness of cosmic reality. They stand as testament to the power of mathematical reasoning combined with physical intuition, pointing toward possibilities that nature might realize in its most extreme environments. As we continue to explore the cosmos with ever more sophisticated instruments and ever deeper theoretical understanding, we edge closer to answering whether gray holes exist among the universe's inventory of objects. That answer, when it comes, will teach us something profound about gravity, quantum fields, and the ultimate behavior of matter under extreme compression. Until then, gray holes remain a fascinating possibility, a theoretical prediction awaiting observational verdict, a reminder that the universe likely holds surprises beyond our current imagination.